Okay, so Mi is called homosymplectic manifold if exists to 0 form omega non-degenerate, and then so M is complex, so it gives what omega to the n is section canonical class. Right. So easiest example is the following one. So if M is Kahler, homosymplectic manifold, then M is hyperkähler. And usually people treat these two notions as synonymous, like hyperkählers and homosymplectic. But there exists some non-Kahler homosymplectic manifold. I will talk about them a little bit later. So if M is hyperkähler, so it means that there exist three complex structures, I, J, K, satisfying quaternionic relations. Yes. And the Kahler forms are closed. Okay. For the such manifolds, we have first thing, the Bogomolov theorem, which in general by the Bogomolov decomposition, it says that any hyperkähler is covered by the product of torus and hyperkähler manifolds with 2-0 part of Bogomology being one-dimensional and generated by form omega given here, homosymplectic form, and simply connected manifolds K. Okay, so such manifolds are called simple, and for the simple manifolds, okay, so second thing, but deformation theory of hyperkählers is abstracted. So that means that Coordinate deformation space is smooth. Okay, so it's true not only for hyperkählers, it's Bogomolov tenth order theorem. It's true in more general case, sure. And the second, that if we have such manifold, like a building block, which is called simple hyperkähler, then we have so the theorem of Fujiki. So M is simple hyperkähler. When there exist form Q, non-degenerate integer quadratic primitive form, and the rational constant lambda, such that for any two form eta, for any form we have the following. So the integral of eta is lambda q computed on eta to the n. And this is Hodge relation. Okay. And the existence of this Beauville-Bogomolov-Fujiki form, so this form is called, so form Q is called Beauville-Bogomolov-Fujiki form. And the existence of this form is following from just from deformation theory. That means that we have the period map from Kurnosov deformation space to the Grassmannian H20, H2, and it says so the fiber goes to homomorphic form eta. And the observation of Bogomolov with deformation, with this, with period map, so local return says that this deformation space is locally isomorphic. So the Fn is locally isomorphic. To the quadric given by form Q. So for Q, lambda 0, 0. Okay. 6. Okay, and we can write this form explicitly in terms of homomorphic form. Let me do it just like so. Q of alpha is n over 2. So m like omega bar to the n minus 1 lambda squared plus 1 minus n omega to the n minus 1 omega bar to the n lambda times omega to the n minus 1. Okay. Omega bar, so omega to the n, omega bar to the n minus 1 lambda. Okay, so it's kind of easy to check what this. So the statement is the following. So we have this period map. First of all, it's immersion. Then we can check what. But if we define form Q in this way, then indeed the image of this deformation space is this quadric, and then we have this local isomorphism. And this is kind of a classic stuff for hypercalars. So today, like I promised to talk about non-Kahler stuff. So let me first start with a theorem. Okay. So theorem. So it's a joint work with Verbitsky. And theorem is the following one. So let M be homomorphic symplectic manifold.
Not necessarily Kahler.
Right, not necessarily Kahler. Of dimension 2n. First of all, admitting Cauchy decomposition on second homology. So it means that any two form is decomposed. So we have decomposition of H2 in the sum of HPQ of a closed forms, and and this is the same that we have in the Kahler case. So it means Cauchy decomposition H2, and that is not enough. And all delta OD exact homomorphic form vanish. Okay, and H20 is isomorphic, is vector space, and the H02 is vector space one-dimensional. Okay, one-dimensional. Then there exists form Q, Beauville-Bogomolov-Fujiki form, that means that Fujiki relation holds. So for any two form eta, we have the integral q computed on eta or to the n. So let's say, first of all, what so this form is bilinear, whatever. But here I don't say about the constant because in general we don't know if it's integer or not. So it doesn't make sense to write a constant here. Okay. So why we need this part? So I mentioned what this implication of period map. It follows from deformation theory, and the deformation theory here we have like the deformation space for hypercurves is abstracted. But it's a more general like situation when we have trivial canonical class and Didi-bar lemma, like Kahler situation. So in non-Kahler case, we don't have Didi-bar lemma in general, right? So that's why we need something to overcome Didi-bar lemma argument, to use Tian-Todorov lemma like without the case when we have Didi-bar. So with condition that all exact homotopy form vanish, and one-dimensional 2 parts, it gives us possibility to overcome like absence of Didi-bar lemma in our case. Moreover, actually, so okay. So let me say like kind of argument why this is true is the same beautiful argument. That's quite the same as in the Kahler situation. So we can take U some local deformation space. We also can shrink with U to U prime such that, so shrinking, such that all homomorphic, all complex forms, all complex structures sitting in U, on U prime, sorry. And then we can consider the Cauchy decomposition on H2, which we have by conditions of a theorem. And this gives us action an action of rho I on H2. And this action is given by e to the 2 pi I p minus q for pq forms. Okay, and then argument like this part is the same as if you work for Kahler case, you have the same argument. When you consider just q, maybe let's say okay, q like this, q tilde, just the following polynomial. Q of eta is eta to n. When this polynomial is just rho I invariant. And then we use just a beautiful lemma here. Lemma deform. So we can consider a huge group which consists of with all operators on cohomology. And then we have just the algebra statement. So let V be a vector space with action of Lie group G, and Q is G invariant polynomial function. S inside of Grassmannian 2V is open. Assume that for any P from S, we exist. Okay, maybe I need more space. So there exists a subgroup, actually of gamma. So there exists a subgroup like rho p of gamma, like isomorphic to S1, acting as rotations. Like on P, and trivially on the quotient. When the statement, when Q is proportional to Q to the n, and where Q is quadratic form is quadratic form on 3. Okay, so I mean the same argument. Quite the same argument works for hypercurrent station. What's difference here? But we set in Grassmannian. So what we are doing here is a period map. We define a little bit different. So we map our M with I, like so the deformation space, like we map it to real part of omega and imaginary part of omega, sitting in Grassmannian of 2H2. And when it says that this image is open, quite the same in the Kahler case. And using this argument, so here we have V is just H2 in our case. Q, so G is a group given by O, rho, I as operators. Q is the same as this polynomial. And then by this statement, we have that this polynomial is proportional to Q to the n. Okay, so it means that even in non-Kahler case, we have, so Beauville-Bogomolov-Fujiki form for some non-Kahler homomorphically symplectic manifolds. And like obvious question, do this like homosymplectic manifolds of this condition exist or not? Do we have any of them? So here I need to mention, okay, in dimension 2, I mean, it doesn't make any sense in dimension 2 because second homology is a middle homology when we have intersection form. But in dimension 2, we have K3. This is a hyperkähler manifold. Yeah, I hope that you know what K3 was, like some quartic in P3, for example. Like Fermat quartic, let's say. And non-Kahler example with the same like kind of the same properties, so trivial canonical class is a Kahler surface. And this is part of Kahler naked specification. And Kahler surface sure is not simply connected. And kind of, and there is no d-bar lemma for Kahler surface. But next step, what happens in higher dimensions? Okay, in higher dimensions we have like planes of hyperkählers. I mean, 2 families and 2 examples, and one series of examples which satisfy with conditions. Okay, so if we just say, if we consider just any like manifold with trivial canonical class, when Bogomolov-Centro theorem doesn't work. For example, we can take a quotient of SNC by some co-compact discrete group, and or some Iwasawa manifolds, whatever, some new manifolds. But here, likely we have this condition, and let me say what. So in hyperkählers, we have 2 examples, like two series, like Hilbert schemes of K3, generalized Kummer, and 2 sporadic examples of a gradient. And the importance of this Beauville-Fujiki form is the following one, but for all these hypercalars, we have a Hodge diamond of cohomology. And we have a group, so we have like Lie algebra SO for B2 minus 2 acting on this Hodge diamond. Moreover, like all cohomology is the sum of models in respect to this Lie algebra, which is like in a complex case of type Bn on Dn. And this 4B2 minus 2 is not just something. Let me say this is like SO H2 plus hyperbolic and Q tilde. And Q tilde is such form that restriction on H2 is Q, and in the hyperbolic part is hyperbolic. Okay. Then here using the fact that Beauville-Fujiki form has signature 3B2 minus 3, and hyperbolic is 1, 1. So somehow we can say that Beauville-Fujiki form determines, I mean, with second cohomology determines the cohomology structure of hypercalars. And it would be beautiful if something like this would work in non-Kahler case. The problem with this like huge Lie algebra consists of like Lefschetz operators, and in a non-Kahler case, it's much harder to work with them. Okay, but let me mention what kind of manifolds satisfy these conditions. Okay, so I hope that you know the Gilbert scheme, some like resolution of singularities of symmetric power, and with the generalized Kummer, I think I need to say something. So I can take a Gilbert scheme of n plus 1 points over torus, 2-dimensional torus. It map to just torus. And this map induced from the following map. I can consider the product of n plus 1 copies of torus. When I have summation map of coordinates to the torus, I have a Banese map. And this map induced some map sigma here. And generalized Kummer is a fiber of this map, so pre-image of 0. Generalized Kummer. So we need to consider generalized Kummer because this one is not simple hypercalar. Okay. Then, like a non-Kahler case, we have Bogomolov-Guan manifolds. So we first will construct by Guan, then by Bogomolov, construction is the following one. So take a Gilbert scheme of n points over S, and that's the Kadara surface. When we have map to elliptic curve, because Kadara is the elliptic fibration of elliptic curve, and also S1 fibration over 3-dimensional torus. And we have map to 3-dimensional torus. So we have fiber of this map, let's say HN. And fiber here is just Fn. And then we can see the following one. So Hn mod e to the L, so the fiber of Kadara surface. So this is a complex manifold with singularities. And we have Fn mod S1. So Fn is real manifold, but after S1 action is also complex manifold with singularities. And when the statement of Bogomolov but will exist manifold like M such that it is non-Kahler, simply connected. So there are points of non-Kahler manifolds, but we need some simply connected with trivial canonical class. So also homosymplexic. And these maps we have degree n. So this map is just ramified covering, and this map is degree n. So and this M, which is called Bogomolov-Guan, it satisfies assumptions of theorem. Okay, so what actually we want? We want to like generalize hyperkähler geometry to non-Kahler case. Sure, we have a lot of things which depends on a Kahler condition, but some of them definitely would work even in non-Kahler case. So how many means do I have? Just 0? 2? Okay. Yeah, I will finish with a conjecture. Actually, even 2 conjectures. So Beauville-Bogomolov-Fujiki form is non-generate of signature 2, 4. And this is different with hyperkähler case. In hyperkähler case, the signature of this quadratic form is 3, B2 minus 3. In non-Kahler case, we have second homology of M being equal to have dimension 6, and by conjecture we have this decomposition of signature. And this is the first. And second one, which I think is quite true, is still try to work out with collision with conjecture. So let's say SYZ conjecture for Bogomolov-1 manifolds. So that any Bogomolov-1 is the Lagrangian fibration is deformation equivalent to Lagrangian fibration. Okay, and I would like to finish with this because I'm over time. Yeah.
Other questions? Well, there will be plenty of time to discuss all this. Well, thanks a lot for this answer.
Okay, thank you.